We've thought about what game theory is, what games are, and we've seen some simple ways of representing games. Now what we want to do is just a tiny bit of game theory. We start with the question, why did that happen? Why did that happen? Dixit and colleagues think that sometimes we can answer those questions by appeal to game theory. In particular, they think that cutthroat competition in business can be explained by realizing that rivals are trapped in a prisoner's dilemma. So their view. And indeed, they're also suggesting, I'll come back to this again later actually, that the prisoner's dilemma structure isn't some kind of abstract formalism, but is something that we observe in a wide variety of different situations involving birds, businesses, countries, and individual human adults as well. So if they're right, this is a kind of significant thing to try to explain. But what is that explanation? Well, first of all, here's the prisoner's dilemma. You can see what happens in the prisoner's dilemma. If we both resist, then we each gain the almost most preferred outcome. The only slight thing that could happen if this is you that would be even better is if you confess while I resist, right? And then you just do slightly better, while of course you've left me in real shtuck, right? And conversely, the game is symmetrical. Very good. So here's the prisoner's dilemma. Take a sec, sure you understand the payoff actions. Rationally, how might somebody respond in the prisoner's dilemma? Well, here's how we might think about it in terms of game theory. This outcome, in a way, is pretty good, right? So if you think about the collective benefit here, this is far better than any of the others. But in practice, we know that many things, people, businesses, birds who are in a prisoner's dilemma situation will get this. That is to say, they'll both confess, or sometimes this is called defect, right? They'll both confess, they'll both defect. So there's a good question. Given that this is clearly more attractive than this, how is it that people in non-cooperative one-off games will very often find that this is the best that they can do, and this far better thing is very often out of reach? Not always, but very often out of reach. Why is it that we so often see that? So that's a good question. That seems like we could answer it. Now, one way to answer it is to think about the payoff structure just for one player at once. So let's take the person who's playing the y-axis, if you like, prisoner Y. So if we think about prisoner Y's resisting, if prisoner Y resists, they either get 3 if you resist as well, or 0 if you confess. But here's the striking thing about the way this game's structured. If they confess, they always do better, right? So they go either from 3 to 4 or from 0 to 1. So regardless of what prisoner X decides to do, prisoner Y is always better off confessing than resisting. Regardless of what prisoner X decides to do, prisoner Y is worse off resisting and better off confessing. So we can say, using the game theory jargon, that confess strictly dominates resist. Confess strictly dominates resist. You see that? You see that. Good. And of course this is symmetrical, so the same thing will be true for prisoner X. Confess strictly dominates resist for prisoner X as well. So here's a very simple thought. If you're in a game and there's an action which strictly dominates another, that means it generates more greater payoffs. You're likely to take the action that strictly dominates. After all, by taking the dominated action, you're guaranteeing that you will lose relative to what you could have had. So this is our first notion, dominance. And the idea is that we can use dominance to explain why it is in situations like the prisoner's dilemma, people often collectively achieve poor outcomes relative to what they might have achieved. Let me show you this one more time. This is dominance. So just think about one of the characters at once. So resist is dominated by confess, because if somebody were to resist, no matter what prisoner X does, they could always have done better by confessing. In each row, are they rows? No, they're columns. In each column, confess does better than resist. So this is the notion of dominance. And I think this is a very plausible and simple idea. It's because confess dominates over resist that those who are playing a prisoner's dilemma will typically end up with this worse outcome when even the much better outcome was available to them. So that, I think, is a useful result from game theory. Now, this notion of dominance then is quite useful for us in working out why people play games in certain ways, why certain strategies tend to come up again and again, and other apparently better overall options are neglected. But there's a limit to what you can do with just that notion of dominance, because not all games do involve a strategy or an action that dominates others. So, for example, consider this game, which is sometimes called Hawk-Dove. You've got two gangsters and they're sitting there in their various rooms and they have a choice, right? So they can either both decide to stay at home, in which case things are going to go pretty well for them, okay? They're going to sell whatever it is, this bad stuff, these drugs that the gangsters are selling. They're dealers, right? They're dealers. So they're selling these drugs, they're ruining people's lives, preying on the vulnerable and people who've, had bad life experiences and so on. So if they stay at home, they're going to do pretty well out of that. They're going to make good money. On the other hand, one of them can decide to go out and attack the other. And if the other stays at home, then what will happen is that the attacking gangster will gain a bit of new territory and a boost to the reputation. So that will go particularly well for the gangster who attacks, and badly for the one who stays at home, but not as badly as if they both attack, because in that case they both weaken themselves, and of course third party is then going to come in and see some more territory, and they both don't look particularly smart in that situation. So this is the Hawk-Dove game. What you notice here is that there is not an action for gangster Y or for gangster X which dominates the other. So let's take a look at this. So here's gangster Y. Now gangster Y could decide to stay at home. In that case, gangster Y is slightly worse off than she would be if gangster X had also stayed at home, but slightly better off than she would be if gangster X had attacked. So we've got a situation where the best possible outcomes cross this action. And similarly for attack. Right? So stay at home and attack, neither of those dominates, not even weakly, the other. Neither of those dominates the other. And the game is symmetrical, so the same thing applies for gangster X. So if we want to understand what happens in this situation, we cannot appeal to dominance. That won't help us. Now, what is it that we might want to understand about this situation? Well, I guess, here's something that we could understand. This is clearly a terrible outcome, the dual attack, right? That's clearly a terrible outcome. And the stay home thing here is pretty good, right? So why is it that very often we get this dual attack thing happening? Why is it that very often we get this dual attack thing happening? And relatedly, why is it that very often people go to extreme measures or very extended measures not to get themselves into a situation where they are in effect playing this game? This is a game that you do not want to play. So if you're a gangster, you do not want to get to the point where this is the game that you're playing. You want to try and improve your situation, do all kinds of signaling and other measures in order to avoid getting put into a situation where this is the game that you're playing. So we don't have dominance, but we do have some things to explain. What are we going to do? Just here, our second notion, the notion of a Nash equilibrium, is exactly what we need. Now I want to show you what that is before I give you a definition, because it's kind of easier to see what it is than to understand the definition, at least for most people. So here's a thought. We're back with our Hawk-Dove game with the two gangsters. Here is one Nash equilibrium. Why is this a Nash equilibrium? We'll just have a look at it from the point of view once more of the Y gangster, gangster Y. Think about what could happen here. So gangster Y controls the Y-axis only. So if gangster Y wants to deviate from this choice, we take this as a starting point and think, could gangster Y do better? The answer is no, because gangster Y can only move on the Y-axis. So if gangster Y moves from staying at home to attacking, things get worse for gangster Y. All right, very good. Now take a look at the perspective of gangster X. Right? So gangster X is over here attacking. Could gangster Y improve matters by acting unilaterally? And the answer to that is no, because if gangster X is acting unilaterally, gangster can only move on the X-axis from attack to stay at home. But that actually makes things worse, not better. So this one, stay home attack, this corner here, is a Nash equilibrium. Why is it a Nash equilibrium? Because neither gangster can improve their situation by acting unilaterally. So this is the notion of a Nash equilibrium. A Nash equilibrium for a game is a set of actions from which no agent can unilaterally profitably deviate. If you've been following along, you probably understand this, but I just want to be really careful here. So the actions are the choices that we've framed for our participants. So in this case, it's attack or stay at home. A set of actions is one course of action for each of the players in the game. Right? So for example, it would be attack, stay at home would be a set of actions in this case. Sometimes those set of actions are referred to as a profile. Sometimes that's a profile of actions. When we talk about profitably deviating, we mean relative to the preferences that the individual agents have. So you know those numbers in the representation of the game correspond to how strongly or weakly the agent prefers one outcome over another. So profitably deviating means gaining a more preferred outcome over a less preferred outcome. And we're stressing unilaterally because the idea is that we hold constant all of the actions that the various players are taking, and then we suppose that one player just decides to change her action only. Does that one player's change, the unilateral change, improve the outcomes for her? Right? If it does, then we don't have a Nash equilibrium. If it doesn't, and it doesn't do that for any of the other agents either, then we do have a Nash equilibrium. It's actually an incredibly simple and very beautiful idea. So if you haven't got your head around this yet, do go back and take another look at what's happening in the Hawk-Dove game. If you do think you've got it, here's a very simple test to check you understand it. Pause the video, take 90 seconds, and answer the question, where is another Nash equilibrium in this game? For in this game, there's not one, but two. Sometimes there's just one, sometimes there are none, sometimes there's many. In this case, I'm telling you there are two. Where is the other Nash equilibrium? And why is that the other Nash equilibrium? Pause the video, take 90 seconds, go. All right, so welcome back. Hopefully you've seen that this is the second Nash equilibrium. If you've seen that, you're doing quite well. A good thing to do is to look at some of the other games that we have considered previously and see if you can spot where the Nash equilibria are for those games, right? Or if they have any. And if you can do that, you're quite confident that you understand this notion well enough. But theoretically, why should the players not expect to settle on a non-Nash equilibrium? The interest that we're going to have in this game is, look, yeah, that's right, let me step back. The interest that we're going to have in this game is relative to that question. Why is it that in this kind of situation, people often end up in a really disastrous combination of attack-attack? And the thought's going to be, well, look, there are actually not one but two Nash equilibria, right? This one and this one. And that makes it extremely difficult to decide what to do. Right? It makes it extremely difficult to decide what to do. Each of the gangsters probably is going to settle if we were to do this where each of the gangsters playing multiple non-cooperative one-off games with different individuals. What they're likely to do is to settle into a strategy where they do mostly staying at home but a bit of attacking, and they try to randomize their behavior to make themselves unpredictable, therefore ending up often with this. That's because this dual Nash equilibrium makes the whole thing unpredictable. But what we're assuming in giving that explanation, which is actually a pretty good explanation of why it is that people in this situation often end up both attacking the most disastrous outcome, and also why it is that you would go to great lengths to avoid playing this game. You do not want to get into a situation where you're playing this game. In order to explain both of those things, we are assuming that the players are trying to avoid the non-Nash equilibrium and to achieve one of the Nash equilibria. right? We're assuming that that's what rational players are after, a Nash equilibrium. But why is that? Why is that the case? Why should we expect them to settle? Why should we not expect them to settle on a non-Nash equilibrium? So to illustrate, for example, this is a non-Nash equilibrium. So what would be wrong with the idea that each of the players were aiming to settle here? Let's just both stay at home and have some peace. And this actually looks pretty attractive compared to this. Right? It looks pretty attractive compared to this. And to be honest, it's probably the best that these two evenly matched players could do. Just stay at home all the time. So why is it that they're not expecting to settle on that? Well, let's suppose, hypothetically, that they were. So suppose that Gangster X actually expected both of them to stay home. In that case, what should Gangster X do? Well, clearly, what Gangster X should do in this situation is attack. Why is that? Because Gangster X controls the x-axis and so is able to move from the situation where they both stay at home to one where Gangster Y stays at home, Gangster X attacks. Right? So that makes things better for Gangster X. So if Gangster X expected this to happen, Gangster X would be setting off and attacking. But of course, Gangster Y is fully aware of the structure of the game, and this is just reasoning about what would be rational. So Gangster Y, if Gangster Y expected this to happen, then Gangster Y would also expect X to attack. Right? But that would be a very, very bad situation. So Gangster Y would want something different as well. The stay-at-home option would not be a good one for Gangster Y. So the Nash equilibrium, you remember, is a set of actions from which no agent can unilaterally, profitably deviate. Where our agents are rational, we expect them to be aiming for Nash equilibria, if they possibly can, because any other point will be one where one of the players can deviate, and then the other players anticipating that will want to modify their responses to respond to that too. So the Nash equilibrium points are points where we have a kind of stable, rational landing ground. Very good. So this is relevant to our aim because you remember when we're thinking about game theory and the decision theory that it's based on, what we're after here, as von Neumann and Morgenstern said, is principles that define rational behaviour for participants in a social interaction and to derive from them general characteristics of rational behaviour. So the Nash equilibrium seems like a useful tool to do this. And the thought we've got is that an action's rational if it's a member of a Nash equilibrium, as long as we confine our attention to non-cooperative games, that's to say games in which the agents are not allowed to agree in advance in a way that binds them what they will do. So have we made progress? Well, so far we've thought carefully about dominance and about Nash equilibria. And those two notions seem to be helping us to understand what it is for a social interaction to go rationally. Now, one of the great virtues of this is that when we first start thinking about a game, if we apply the tools of decision theory only, then we seem to get into a kind of loop. Because in a game like the hawk-dove game, how I should act is a function of my preferences and my beliefs about how you will act. But your beliefs about how, my beliefs about how you will act are also going to be a function of your knowledge or expectations about my beliefs and preferences, and about my beliefs about your beliefs about how I will act. And so it goes on. So we get into a kind of regress here, where in order for me to work out what I think the subjective probabilities to assign to your actions are, I have to think about what you expect me to do, but that in turn is a function of what I expect you to do. And so we go around in this beautiful circle here. What's glorious, what's beautiful about the ideas of dominance and the more general idea of a Nash equilibrium is that it allows us to think about the rationality of social interactions, cutting out the need to evaluate subjective probabilities at all. We can say more generally that we should act by avoiding dominated actions and also avoiding points which are not Nash equilibria. So we've greatly simplified the problem of characterizing rationality in social interactions relative to a starting point where we just had decision theory. That looks like great progress.